So I have been discussing Shor's algorithm for factorization, and it has many ingredients. So I will first just summarize the ones which we have gone through and then continue further. So first thing you have to remember that this is a probabilistic algorithm. It's not guaranteed to succeed every time you run it, but you run it a few times and there is a reasonably large chance that you will have an answer. So the first thing was reduction to period finding problem. This is a completely classical procedure, and it involves algorithms for GCD and prime power testing, and the scaling of the algorithm is log n cube. The second step was convert the fast Fourier transform to a quantum Fourier transform circuit, and it's done quite straightforward manner using only Hadamard gate and phase gates with various powers, and the complexity of this thing is order log n square for the every execution of the circuit. It's simpler than that for whatever it is worth. Okay. The third step was modular exponentiation. Of unitary matrix, and that is done by repeatedly squaring the matrix U and picking out the factors which appear in the binary expansion of whatever power you need. So this again has a complexity. It requires basically squaring of a number. A squaring of the number scales as the number of bits, the whole thing squared, just ordinary multiplication. And then you have to combine it with many factors which appear in the binary expansion of the exponent, and that requires how many different bits are there in the exponent, again another factor of log n, and that complexity of that again log n cube, log n square for squaring, and there are so many different bits in the exponent, they have to be multiplied together, another factor of log n. So this is actually again similar to this, but not as good as the Fourier transform. The fourth step, which I described, was phase estimation algorithm for a unitary operator. And what does this algorithm do? Well, it combines the modular exponentiation with an inverse Fourier transform to give the eigenvalue of the unitary operator. This was the last thing I described in the previous lecture, and it has finite accuracy because the eigenvalue can be some arbitrary real number as far as the phase in the exponent is concerned, but this algorithm will be run for some log n number of bits, and you will get so many initial digits for that particular procedure. So this is combines this modular with the QFT inverse. So I described it partly in the previous lecture. Today I will fill in the detail about the accuracy of this particular procedure. Okay. So what is the unitary operator? We just defined as say some u, and it has some eigenvector small u, and the eigenvalue is guaranteed to be a phase because it's a unitary operator, and phi is the phase which you want to calculate, and that has approximated by what I call phi tilde, and it has a binary expansion. I was using the bit labels going from 0 to j minus 1. Okay. So this is not the same as that, and so you will get an approximation, and you have to find out how good that approximation is. And of course, if you want to improve the accuracy, you have to increase the number of bits in whatever that expansion is. So first of all, what we did in that algorithm is create a uniform superposition states. So it was so many components going from k equal to 0 to 2j minus 1, and the eigenvector I'm just going to label for k as a unit vector in direction k. And of course, when I did that, I did it using Hadamard operator, so there will be normalization factor. So it's just a uniform superposition of all k, and then I have conditional execution of this modular exponentiation. With given the k, it will generate the power u raised to k, and the whole thing will act on this u. So this is nothing but modular exponentiation acting on a particular eigenvector. What is the answer? Well, we know the answer quite straightforwardly because of the definition of u is just this, so it is again a sum over k normalization e raised to 2 pi I k phi k and u. Nothing complicated in that. So this was half of the phase estimation algorithm, and now I apply QFT inverse on this particular state. What is the index on which this QFT inverse is going to act? It is going to act on all the bits which are labeled by k, because there were so many different number of bits in the register. In particular, I was using j bits with 2 raised to j possibilities, and the result is, well, I just have to put in the corresponding factor. So this another factor will come. The sum over k is still there, but now I have a new index which is nothing but this phi tilde, Fourier conjugate variable to k, and then the result is the u is just a spectator, nothing happens to it. And for the k variable, I will get a phase 2 pi I k phi tilde, that is the Fourier transform consequence. The sign is opposite because it's inverse. Phi has one phase, phi tilde has another sign. And now there is a dual sum, which again, both of them go from 0 to 2 raised to j minus 1. So the job is done. This is actually now expected to give you the value of phi tilde if you perform a measurement. Okay. So this is a complicated looking structure, but I can ask what will happen if I measure phi tilde. There is a sum over 2 raised to j possibilities. I can get any one of them. Okay, so, but there is a probability. of getting one particular value of phi tilde. What is it? Well, it will be nothing but the coefficient of that particular component. Standard quantum mechanics. And what is that coefficient? Well, we'll write down all the terms. With this thing sitting in front. What is this? You stare at it for a while and then you realize that it can be evaluated very easily. Why? Because this is just a geometric series. The power k is linear in the exponent. Well, let's sum it up. So, if you sum geometric series up to some order n, then it will be, say, 1 x square up to x raised to n. It will be x raised to n minus 1 divided, x raised to n plus 1 minus 1 divided by x minus 1. The standard formula for geometric series. Here, it will be e raised to 2 pi I, the largest power plus 1, which happens to be 2 raised to j. And then just the ratio of the geometric steps. Because of the Fourier transform, will bring another factor of 2 raised to j by 2. This there is a sum over k, but now there is also a sum over phi tilde. It is 1 over square root of the number of dimension. Okay, so we got rid of the summation. Now let's make this thing simpler by realizing that this is exponential minus 1. I can factor out the kind of a common phase to make this factor real. And then this will get converted to some e raised to I theta minus e raised to minus I theta, which is a sine. So now this is 2 raised to j. Sine square half the angle Okay. So this function is well, something which you may have seen before in some context of quantum mechanics, particularly Fermi's golden rule. But otherwise also it's easy to work out what it looks like. Okay. First of all, look at the value at phi equal to phi tilde. The angles are small, so it will be just sine of epsilon approximately equal to epsilon. You remove this sign and cancel out all those things, and this is the square here. from outside. It will become 2 raised to 2j, which will just cancel with this. The value is 1 at phi equal to phi tilde. On the other hand, when phi is even slightly different phi tilde, it will rapidly fall to 0, because this 2 raised to j factor is sufficiently large. So if I take phi minus phi tilde as 2 raised to minus j, the numerator will fall to 0, while nothing much will happen to here, which doesn't have factor of 2 raised to j. So it's a function with a peak at 1 and then falls rapidly to 0, and afterwards it becomes relatively small after that first peak. And so this is actually form of delta function in the limit j going to infinity. If j is really large, then it will have delta function at phi equal to phi tilde, 0 everywhere else. But in general, it has a width, and the width is basically 2 raised to j. Let me get the exact form. So where this numerator goes to 0. It's a peak over here, and you can calculate it, and actually it is not too complicated to sum this quantity over all the value of phi tilde, which has to come out to be equal to 1 by definition of a probability, which is all the normalizations of that. So it has a height of 1, the whole thing integrates to 1, and there is a sufficiently small width, and it's normalized, and that becomes a delta function. So now if I want a more and more accurate value of phi, I just have to increase j sufficiently, which is how many bits I keep. And then the difference between phi and phi tilde will go down. Yeah. Yeah, so if I take the limit where phi goes to phi tilde, okay, sine of a small angle is equal to the value of the angle. So this goes away, all the sign in front, various factors cancelled out. There is a 2 raised to j, there is a square here which will exactly cancel that. So the normalization is 1.
Again, if the phi minus phi error is equal to 2 power minus j, which is also very small, then only the numerator goes to 0.
This, it doesn't go to 0, this one goes to 0 much faster because of the 2 raised to j in front. Whatever it is, when you can plot it in as a function of phi tilde, this goes to 0 when phi minus phi tilde is 1. This goes to 0 where phi minus phi tilde is 2 raised to minus j.
For both the cases where peak is happening or 0 is happening, we are considering phi minus phi error is going.
Yeah, so remember this is not arbitrary, so phi the way we have normalized it, they are in the interval 0 to 1. They are not going outside. The Fourier phase convention, phase goes from 0 to 2 pi. So, and I have done this decimal expansion, there is no integer in front. So these numbers are not going to go outside 0 to 1. Okay, except that the numerator goes to 0 much faster when phi differs from phi tilde than the denominator. Okay, so this is a point to remember. It is connected to the fact that when I run this Fourier transform circuit, how many bits of precision I keep, and it tells you that if I want a probability with sufficiently large magnitude, I must take j of the order of log n. It will come out to be that. This is just expressed as j, but it will come down to the number of bits, how many bits you keep, and that goes back to the number you are trying to factorize. Okay. So this is phase circuit if you are given the eigenvector exactly, but so if I am not given a particular eigenvector, but some superposition of it with coefficient Ci, then you will get, because it's a linear by adding all those bits, for every component you will get the corresponding phase of the eigenvalue. That is just a kind of trivial observation, but we'll need to keep in mind that this is a circuit which is a linear circuit. If I give an exact eigenvector, I get the corresponding eigenvalue. If I give a superposition, I will get a superposition of the eigenvalue. Okay. Now comes the question about going back to the factorization problem. I don't want any arbitrary unitary operator, though the phase estimation works for any unitary operator. I want a unitary operator which helps me finding the period finding problem. It's not just arbitrary function. So I need to choose a suitable operator. And what does the period finding problem involve? It involves taking power of some function. Where x is some set of integer, and when x is equal to r, this function will come back to 1. That is the periodicity. X equal to 0, it is equal to 1. And so we want this particular function. And it can be implemented in this language as a unitary operator If I act once, it multiplies by A. Act twice, I will get higher power, whatever it is. This action, that action is not same. So, it doesn't matter. Now, all it's doing is just a multiplying by the constant A. Why it is unitary? Okay, because multiplication in general is not a unitary operation. Here, everything will fail if this implementation is not possible. And here, the multiplication can be expressed as a unitary operation. So, the condition which allows you to do that the inverse for this thing must exist. And inverse of UA exists because of something which we assumed in the period finding problem, that is A and N are co-prime. This was something which we went through. The test was just run Euclid's algorithm till you get a remainder equal to 1, the GCD equal to 1, and then these two numbers are co-prime, and whenever the integers are co-prime, you can find the inverse. That is a simple logic, just invert the Euclid's algorithm backwards and evaluate everything. So that condition now is used so that this operator, whatever it is, it has an inverse, and you can implement this multiplication operation in a reversible fashion, and no problem with that, and you can call that operation as your elementary unitary choice, which is going inside this phase estimation algorithm. Okay. So now let us see what happens with all this kind of procedure. This is a unitary operator, and that gives you nice identities which will allow you to find the period. Okay. We know there is a periodic function that is raised to the power r. R is the notation which we are using for the period, that is equal to 1. So eigenvalues are you can very trivially write down the eigenvalue is a phase, r's power is 1. So what is the eigenvalue? Well, r's root of unity. Yeah. So this is a place where the input, that it is a periodic operator, has gone in, we all know the structure of the eigenvalues, except that we don't know what the value of R is. Whatever the R is, it must have this particular structure. So now comes a little bit of interest, that you can not only have the eigen value, but you can also write down the eigenvector. And may not use the k. I am going to use somewhere else. Let me call this number S. Okay. What are the eigenvectors? We can write this down explicitly. The only thing is we don't know what is the value of R. But because this is all trivial roots of identity, everything can be just written in a very simple fashion. It has so many different components, and I can write US is equal to 1 by root R, and here I am going to use this So, and this just shows you the eigenvalues are also uniformly distributed around the unit circle, and the eigenvectors will be corresponding directions or corresponding superposition of this particular type, and it's very easy to check that. If I do this, the eigenvalue is equal to 2 pi is kr, and then the only term will survive is a trivial result what will come. So okay, it has to come back to this, and to check it well, we have to operate on this by UA. The job of this thing is to multiply whatever the argument is by 1 more power of A. And here it is A raised to K. You operate it, it will become A raised to K plus 1. But K is all summed over the unit circle. So K plus 1, I can translate it to K prime and separate it out over here. That this will become, if this is K prime equal to K plus 1, this will be K prime minus 1, and that 1 is the factor which is going to sit out. The other stuff is 2 pi is K prime summed over all these factors, and these are all phases uniformly spaced around the unit circle. The only place where you get a non-zero answer where the exponent is 0. Then all the phases add. Otherwise, you have uniformly spread unit vectors of phases which adds up to 0. So only term which survives is actually k prime equal to 0, and that produces this particular result. K prime 0 equal to 0, this whole stuff is going back to the original vector. Anyway, if you have not played around with this kind of jugglery, just try it out. It's not too complicated, and this is just a verification that this is actually the exact eigenvector with the correct normalization.
There could be a, like for corresponding to k equal to 0 also, there could be something on the other side of the circle also. Why is it that we are saying?
Now the extra stuff will remain this exactly the eigenvalue which you use.
That is we are factoring out.
Yeah.
You said that all the others get cancelled out because they are corresponding.
Yeah, that is means things like this, that e raised to I, there's a 2 pi actually. Let me call it A and B. Okay, summed over A. Uniformly spaced around the circle. This is not 0 only when A equal to 0. Because they are all phases around the unit circle, and since they are equally spaced, any non-trivial stuff appears over here. It will add up to 0. The only way you will get non-zero term is exponent is 0, all the terms are equal to 1, and they add up to 1. Some normalization which takes care of this stuff. So that is just a result coming from the fact that this operator is periodic. Our job is to find the period, but we know both the eigenvalues and the eigenvectors in terms of the period.
Here, smaller has to be odd. Here, smaller has to be odd number.
It's the period of this particular function.
It may be even number also.
It may be even odd, whatever it is, doesn't matter. That we have to go back after figuring out the answer to the problem. It satisfies the condition which was put inside this original reduction. If it doesn't, you have to run the whole algorithm again with a different value of the base. But without doing the R, we cannot construct either the eigenvalue or the eigenvector. So our problem is not solved because we have to give an input which we know precisely, irrespective of whatever that value of R is. And here comes another identity following from this same result. So normalization. What is this particular quantity? Uniform superposition of all the eigenvectors. Go and look again at this particular structure. Remember this identity I'm summing over S. And there is a sum over K which is uniformly spacing around the circle. The only term which survives is the one with K equal to 0. Otherwise, S will have various kind of different terms. And what is the term with K equal to 0? Which is A raised to 0. That is 1. Irrespective of whatever the value of R is. And this 1 over root R, 1 over root R, they will all cancel out because when the phase is 0, this factor becomes 1, and there are R terms, and that cancels with this and that to make 1. And this is a state we can prepare without hesitation. This is the number 1 represented in the binary notation. So now I take this period finding circuit, initialize this vector u to be 1, run the whole circuit, some uniform superposition of all those things is, and I will get superposition of all the eigenvalues. So and it's a uniform superposition. What I will get is a phi tilde and phi tilde was S over R, some approximation to it. Okay, that was the phase which was sitting over here. And all values are S are equally likely because it's a uniform superposition. It doesn't give you R's yet, and it can be a complete failure also. For example, if S turns out to be equal to 0, you don't learn anything. So it's a probabilistic, but S turning out to be non-zero among these R values still a large enough possibility. So then the question comes, how do I find R? All I have is this particular ratio. And it can also happen that even if I determine this ratio, and there will be other peculiarities also, as S and R can have common factors, in which case what you will determine numerically is the common factor will cancel out and the denominator will not be R, it will be something smaller. So those are the cases where you have to do something more. either run the algorithm again or find some other strategy to figure out how the R is. I will come back to that. But the question is that is there a way to determine R from this particular ratio, assuming that S and R are co-prime, so there is no common factor cancellation between numerator and denominator. The probability of these two randomly chosen numbers to be co-prime is sufficiently large, at least 60% or so, as I evaluated in the earlier lecture. And here comes yet another result from number theory, that actually by knowing this particular ratio to sufficient accuracy, you can calculate R. Okay. The peculiarity of this thing is that the denominator, all these things are the way we have constructed it. It's this representation of a number in a binary expansion, and so this tilde number, if you write it as a fraction, the denominator will always be power of 2. There is no guarantee that R is a power of 2. So all these peculiarities there, and yet you want to find out what is R from this limited knowledge, and here comes another results from number theory. It's called continued fraction expansion.
So why is that R a power of 2? Why could be?
Not R, the tilde form, because it is written like this. It's a binary expansion with a fixed number of bits.
That is S by R.
Yeah, S by R. I'm not saying R is a power of 2. The denominator of this particular quantity, whatever it is, denominator of phi tilde is a power of 2.
There's no. This would not be
This is a fractional number, no? If it is just one digit, it will be 1 over 2. The 2 digit will be 1 over 4.
And that is also not guaranteed. That is also not guaranteed.
Yeah, R is, denominator of this quantity is a power of 2, but R is not going to be power of 2. It could be anything. Okay. So, what is this continued fraction expansion? It just what to call iteratively writes And the best ways to explain it is just give an example. So suppose I'm given some fraction. Okay. What is the continued fraction expansion of it? Well, what I do is separate the integer from a fraction. That is kind of trivial stuff. And then make the numerator 1. Now, because this was less than 1, you have something bigger than 1 in the denominator. Again, separate the integer. Okay. So it is 2 plus 1 over 2. And here you can stop because the numerator became 1. But you can still go further. One step that is always possible. So it is 2 plus 1 divided by 1 plus I can write it as 1 divided by 2, and the 2 can be written as 1 plus 1 by 1. It doesn't matter. It's not necessary. You can stop here, you can stop here. They are equivalent. But this result is called a continued fraction expansion, and it can be done for any fractional number. Okay. No problem. And how will you work it out in arbitrary case? Well, all you are doing is you have two numbers, and you are dividing the larger number by the smaller number. Whatever it became, you rearrange it and divide it until you hit the remainder equal to 1. And we have seen this algorithm before. It is nothing but Euclid's algorithm for finding greatest common division. Two numbers, divide the larger by the smaller one and continue till you hit 1 at the end. So this is achieved. You don't need a new algorithm. So some fraction will come out. Okay, denominator is some power of 2. Doesn't matter. You can run this continued fraction algorithm, and whatever fraction came out. And now, what is the results from number theory? This is the integer part, largest int. When you evaluate this log n. That you have to evaluate this result, it's a truncated version, how many bits you need in that phi tilde expansion. The number of bits is 2 times log n plus 1. That will be the value of j which you are going to use. And if you are able to do that, then you can determine r. Okay, this is a statement. What is the formula? Well, the formula is actually given by this particular statement, then let me So if the difference between the exact value and some truncated version which is re-expressed as the continued fraction, if difference is small, then whatever this unknown is, it is now the exact value of s over r and not s over r tilde. It will be bounded in such a fashion. Not only that, it's a convergent. What is the meaning of a convergence? So, they are obtained from taking this expansion and deleting the last bit one at a time. So I will go back to the this series. I will not worry about that outside one because all these numbers are going to be less than 1. So that number was only 2 over 5. What are going to be its convergent? Well, I will delete this last one part and evaluate whatever is remains. Then it will be 1 divided by 2 plus 1, which is 1/3. Then I will delete this whole stuff, and whatever remains is a half. And then the last bit is just remain, delete this whole stuff, which basically gives me 0. That doesn't mean anything, but so the point is that you will get these numbers which are truncated values of this continued fraction expansion, and those truncated values are called convergents, and those truncated values will give me the exact value of S over R, provided this condition is satisfied. So in this particular case, 1/3, 1/2 are some approximation to 2/5. They are the truncated versions obtained by the conversion. One of them is slightly below, the next one is slightly above. They kind of alternate, that also happens. But those will have the exact values, and here the exact values are not necessarily restricted to the denominator being a power of 2 once you started truncating these last bits. And R can actually appear directly inside that expansion. Now, what is the proof of this statement? As I said, it's a property from number theory, and it's given in the appendix of the Nielsen-Chuang book if you want to verify it. But it's a guaranteed result. So what we need to do is somehow guaranteed this particular statement that I want to determine this fraction to this accuracy. Now R is, by definition, cannot go more than n. It is a period, well, you can make it equality if you like. It cannot go beyond it. So I can guarantee this is satisfied by evaluating this quantity to this many number of bits. Okay. Instead of 2r square, I put 2n square. How many bits are needed? This is exactly the number of bits for 2n square. So that fixes all the counting procedure about I'm going to run a circuit up to a finite precision. That number turns out to be log n, the number I'm trying to factorize, and the various ingredients have different kind of complexity, and this continued fraction expansion, well, how many steps it will use, it is again specified by the Euclid's algorithm, which is the same one which we use for GCD. So it's a classical stuff you do at the end after getting this estimate of phi, but the complexity actually not or this, but the continued expansion itself. Now, why the log n came is because we needed so many number of bits. So this now actually specifies a whole algorithm. You are going to run it with initial state, which goes into this phase estimation, how many number of bits are there. They are all specified. You take the powers, you do all the superposition, get an estimate, and from that extract the value of R. And yet with all this effort, the algorithm is probabilistic. There are some cases which will fail. Okay. So when the algorithm fails, okay, how will you know that the algorithm fails? Because verification of this problem is easy. If I get a value of r, checking that a raised to r mod n is 1 or not, it's not a difficult job, because it's all just a multiplication. So I get an answer for r, I have to verify it. And failure means that the verification didn't succeed. Then a raised to r r didn't turn out to be an even number, whatever it is, various things. The choice is, I'm calculating powers of some number a, it didn't work, choose a different value of a, run the whole thing again. The only thing which allows this to succeed is the success probability is reasonably large. Sometimes it fails, you have to go through the whole thing again, but the probability is bigger than half in all the cases. So on the average, maybe 2 or 3 trials you have to do, and then everything is fine.
Can you once again explain how from the convergence topic we got the R value?
Yeah, so R will be the denominator. It will exactly give you S over R.
Addition of the denominators of the convergence.
Yeah, so you have to look at the denominator of the convergent and check whether that satisfies this particular constraint.
And for any different A, the initial state is prepared in the same way, or the initial state is same.
Yeah. One can try various things. First of all, since these are some bounds, sometimes you get a value of r, and maybe because some error, it went a little bit off. So whatever r you get, you try r plus 1, r minus 1, whether it has a success rate, sometimes it works out. But those are all, I mean, kind of okay. Something which you don't want to run all over again, one can check. R plus minus 1. That is one possibility. The other thing which can happen is you got this answer, but it could be that something in the numerator and something in the denominator had a common factor and it cancelled out. Okay, then you will not get an R, but you will get something less. Then what do you do? Well, you will have to still run multiple trials, but the one time you will get R1, the other time you will get R2 because something got cancelled out. And from that you can construct R by something which we learned again in school. When adding two fractions, there is no something cancelled out, you find a common denominator. Okay. And that is known as a least common multiple. And if something cancelled out, well, you multiply it and check that one also, whether that is the correct result. also, so that is called least common multiple of two candidates. Maybe it will work. It can help. But the question is, how do I find a common denominator of this kind of object without factoring? Okay, factoring is a bigger problem, but this obeys a very simple relation that what is the least common multiple of any two integers is the product divided by the greatest common division. And this is something we have seen over and over again. Euclid's algorithm does it.
And the LCM part comes out when S and R gets cancelled out, right? When there's a factor.
Yeah.
R is a factor.
So if something has cancelled, then you can try this least common multiple, etc. So there are all these simple-minded ways to improve the efficiency of the algorithm, but the general statement is that it is a probabilistic algorithm with not too many number of attempts, and you will get the result. So that's essentially the story of the factoring problem. And people have basically tried some things to improve the behavior, and there are many different tricks. One of those things I can point out that many of these classical algorithms, which are all this log n power cube, and they came from multiplication of two integers essentially. And there are fancy ways of doing the multiplication. So I will just point out the results, not it can help a little bit, because the Fourier transform stuff which I pointed out is only log n square. The multiplication which are giving one more power. And this small n is the number of bits, little bit easier to this is just a curiosity in terms of various procedure, but you can actually reduce this n cubed to n square log n, etc., etc. It's a matter of detail. But this is well, the story of Shor's algorithm. Okay. Lots of ingredients were buried inside it, and it's kind of remarkable that Shor knew all the ingredients which were needed to be put together, and that's how we came up with this algorithm. The point which went in essentially was the periodicity of the function, and that is being exploited, and that it can be contrasted with the Simon's algorithm, which I had it's periodic over the smallest fields at 2 to the power n, and Shor's expanded this thing to some integer, you can call it r. And that's all that happened, and it solved this kind of important problem, which is heavily connected to cryptography. I have not said anything about cryptography because that requires another bunch of exercise in number theory. How does knowing the factors can be used to make a code? Okay. And so it's application, so based on the RSA scheme. It uses a function well known in number theory, just called phi of n, constructed by Euler, and what does it mean? It counts number of integers which are between 1 and n and which are co-prime to that particular integer. So all this co-prime business is involved inside there also to everything, but if you know this function, then you can construct that RSA code. That's essentially the point. And constructing this function is non-trivial in general, and the cryptography scheme actually exploits it. But I'm not going to go into the exercise. I'm just mentioning that this is what allows you to build a particular code. Okay. One more thing I can mention, which is also a topic which mentions other results similar to Shor's algorithm, and that is something called a hidden subgroup problem. And Shor's algorithm solves this problem for particular type of groups. Okay, so the result is that it can be converted that whenever the group is abelian means commutative, the Shor's algorithm will solve this problem. this group is abelian. It's the integers, multiplication is commutative, nothing complicated in that, and it generalizes to this. But the situation where the group is not abelian, non-commutative, it's an open problem. People have tried very hard for now 30 years. Nobody has succeeded. Okay. So non-abelian groups are a different category compared to the abelian groups as far as this hidden subgroup problem is concerned. And I can give a simple-minded definition. This is just for, again, curiosity of what that thing is. So the definition, I take a group G and a function which is defined on every element of the group. Okay. What does this problem say? That this function has a particular property. In this case, it's just a periodicity. But the function now is written as a little structure. So we have to convert it to a unitary notation. So it has a unitary operator. That is, f of g is implemented by some unitary operator, and the hidden subgroup allows you to implement this function as the second register, you add the whatever the value of the function is. So it's a unitary version, and inverse is you did twice and this thing will disappear. Okay. So you have this particular function. Now the property of the function is requires as well the function is a constant for k so there is a subgroup of this large group on which the function is constant, the same value for every member of k. But k is a subgroup, so then there will be factors. How many times and this is something which comes from the group theory, that if you are given a group and a subgroup, you can construct cosets. And for finite groups, the group breaks up into an integer number of cosets. And what the function is that on each coset, it has a different value. the job is to find k. So and that is a periodicity problem because k is a subgroup. So k will always have an identity element which doesn't do anything. An identity element is like here a to the power 0 equal to 1. And instead of just repeating after r, it will repeat for all the elements in k. So this is just a statement of the problem, and what we want is a complexity should be polynomial in logarithm of the number of elements. Remember, here the number of elements was of the order of n, or r here, which is so many number of bits in the digits, and this log g is a number of bits required to cover those many number of elements in the group. So this is a problem. Hidden subgroup. Find this function with some certain property of periodicity using effort which should be polynomial in the log of the number of group elements. And Shor's algorithm solves it whenever the group is abelian. For non-abelian, it is not solved. And the reason is interesting. The periodicity stuff, whatever it is, you can define by Fourier transforms, no problem, for arbitrary groups. What is missing, that you have a periodicity problem, you can solve everything which is equivalent to solving for this S by R tilde using effort which is only polynomial in the number of group elements. The part which fails is determination of R from knowing this particular fraction. It is this continued fraction expansion result which has no analog for non-abelian groups. Nobody has found that analog. So it's actually a breakdown not of the quantum part of the algorithm, but this classical reduction is not there. And that's why the problem is unsolved.
So the S by R does not follow this equation. S by R minus phi.
This result doesn't, there is no analog of this result for non-abelian groups. Fourier transform works. There is no analog of and that is the place where the story has remained. People have tried all kinds of tricks, but nothing has succeeded so far. So, yeah. I think this is the place to stop talking about all kind of things related to Shor's algorithm, and from next lecture onwards, I will go back to another property which is important for learning quantum theory, and that is the study of quantum correlations. All these things are possible because there are peculiar quantum correlations, and those have been demonstrated well. A particular example is Bell's inequalities, and now it has even a Nobel Prize to go with it. So of course it's an important topic, and give you some idea about how the features of quantum mechanics produce peculiar kind of correlations.